Hello everyone, this is Rohollah. I'm a PhD student at Glasgow Caledonian University. I'm going to present a paper forms part of the wider research study directed to explore the effect of superabsorbent polymer SAP on microstructure development in early age of fiber reinforced mortars containing supplementary cementitious material. This work is supervised by Professor Agnes Naukle. Supervised cementitious materials such as fly ash and GGBS have been successfully used to improve sustainability of Portland cement materials and by reduction of clinker responsible for high CO2 emissions during its production. However, early age shrinkage of cementitious systems is still a major concern. This is due to a slow reaction of the SCM in early ages, and the physical presence of SCM is known as a filler effect to affect the rate and extent of the reaction of the SCM clinker component. This is led to increase the capillary pores and consequently increase the autogenous shrinkage. In order to mitigate the negative shrinkage effect, polymeric fibers are commonly used as widely documented. Incorporation of the fibers into cementitious matrix can effectively improve tensile strength and mitigate early age cracking by providing fractional bond with cementitious matrix. However, their efficiency is often limited, especially in the large surface element or in severe environments. The addition of this fiber introduced air voids and more pores, which compromise compressive strength. Therefore, some form of internal curing is still required to decrease self-desiccation and promote cement hydration. Superabsorbent polymer SAP is a natural or synthetic water-insoluble three-dimensional network of the polymeric chain cross-linked by chemical or physical bonding. They are able to take up a significant amount of fluids from the environment dispersed throughout the structures. SAP have a potential application as an internal curing agent for concrete and mortars. Its high capacity to absorb water from fresh mix and release it over time can control autogenous shrinkage in early ages. Additionally, when SAP collapses, it leaves behind pores that can significantly change microstructure of hardened concrete and eventually more rooms and provide more rooms for later product disposition. Therefore, we look into analyze the effect of SAP, and the main objective of this paper was to evaluate the effect of SAPs on microstructure development of fiber reinforced mortars containing SCM. Therefore, the microstructural analysis are supplemented by the analysis of the elastic module of composition. Since the effect of SAP in cementitious matrix depend on the number of parameters such as the polymer shape, size, cross-linking density, chemical structures, and ionic concentration of surrounding pore solution, three types of the SAPs with different particle size and different water absorption capacities were analyzed. Three types of the cement have been used in this study. Same one Portland cement, same two Portland with fly ash, and same three Portland with the GGBS. 15 different compositions of fiber reinforcers were assessed at the 7, 14, and 28 days by MIP and SCM techniques. The elastic module also were tested up to 365 days. As you can see, in this figure, sub A, sub E has a smaller particle size, and sub A and sub C have particles in the same size range. However, sub C and sub E have similar composition. Water absorption capacity of SAPs in three cement pore pass solutions have been determined by T-bag method. Sub E, as you can see in these three figures, sub E had the highest absorption capacity, while the lowest water absorption were recorded for the sub A, and a more stable swirling behavior in cement filtrate solutions were observed for sub C. These three figures. Here some example of the different pore size distribution in studies fiber reinforcement are shown this here. In early hydration stage, SAP samples had a similar PSD pattern compared to the free SAP samples. However, at the 28 days, the number of the smaller pores under 20 nanometer was reduced in sub-samples. Well, in the reference sample, this amount has not been changed over the time. MIP velocity obtained for samples with GGBS is significantly larger than for the fly ash and Portland cement samples. However, as you can see, the total porosity values increased during the first 14 days. With the progress of hydration after the second week, the total porosity is slightly decreased. This effect is more evident for samples with SAP E, and the water release from the SAPs facilitate the formation of the hydration product and filling up the existing pores space, which in turn result in densified microstructure at later age. The SCM analysis as well shows here some of the example. As you can see, formation of the large void by SAP can also have an impact on the surface roughness. The samples with SAP C, actually SAP C, seem to have the larger pores, especially for the with the SAP same tree with GGBS. It's likely that the high water absorption capacity and large particle size for this polymer has caused formation of the pores of such a big diameters. The overall trend of elastic model up to 360 days of the is shown in here. In general, the elastic module of the mortars increased over the time due to the progress of the hydration reaction. The result showing that the elastic module for SAP modified sample was lower than for the reference mixers. However, the negative effect of SAP addition is more marked at the early age, in the 14 days, and is a slightly decrease at 28 days. However, this effect is reduced later. You can see later due to further hydration facilitated by internal curing of SAP. The decrease in SAP mortars can be related to their higher total porosity at early age. Pores may act as a weak spot and influence mechanical behaviors. In majority of the samples, SAP A with the lowest water absorption capacity had the highest elastic module values at early age, due to 14 days. It should be also considered that SAP E with a smaller particle size had the lowest influence on elastic module behavior, and further enhancement were observed in blended cement due to reaction of the SCM with Portland cement hydration. And this new product of secondary hydration have subsequently filled smaller pores under than 20 nanometer, as seen in the previous figure. Based on the experimental result, the following can be concluded. Both MIP and SCMIs confirm positive effect of finer particle size on absorption characterized from SAP E. After the second week, the number of the smaller pores under 20 nanometer was reduced in SAP mortars, and this effect is more evident for the SCM samples with SAP E. SAP E had the lowest influence on elastic module, and we can conclude that the finer SAP particles more efficient in hydration process and more homogeneous internal microstructures. Thank you for your attention.